You know what? So today is mostly going to be a little bit of chalkboard work, and then we will be doing our discussion of our introduction to quantum programming. So I just wanted to make sure, did everyone get invitations to join the IBM Quantum? Yes? You have managed to join?
You have to make like the IBM.
Yeah, I think you do. I think you do. Yeah, I mean, I sent it to your email addresses, but I think to actually use the service, you have to make IBM IDs, authenticate, and all that stuff.
Yeah, it's something like the institution might also provide those type of
We don't have it. Yeah. Okay, so before I get started, let me think what else. Okay, so I don't think anything else. Here, so I'm the only one wearing green. So, oh, right, I have one more. Just throwing that up. Okay, so in the last class, at the beginning, or at the very end of the last class, I talked about the no cloning theorem, correct? So everybody, anybody remember what that was? What was the statement of the theorem? Yes. You cannot copy. Yeah. Excellent. So, you know, think they're too small. Can people in the back read what I've written up here? Sorry, I sometimes end up writing things smaller. Okay. All right. So this is our theorem. I already discussed some implications and applications of the theorem last time. So one of the implications, of course, was something like an unlearnability of an unknown quantum state. We can't fully learn what's in the quantum state if you only have one copy of it. But I also described if I have a billion copies, I can, of course, just measure each of the copies and figure out what the probabilities are. Remember, any unknown quantum state, time is sum A 0 plus B 1. Right? Where A and B are the amplitudes in the 0 and 1 state and represent the probabilities to be in the 0 and 1 state. Right? So A squared and B squared are the probabilities. And so what we're saying is we can't fully learn what A and B are with just one copy of the unknown quantum state. If I give you a billion copies, I simply measure all the copies, and I then measure A squared and B squared, and therefore I know A squared and B squared, and then the only thing remaining is the phase between them. And that phase can be calculated by one other experiment where we say create a superposition and then measure it, or measure in the superposition state, so to speak. Okay. So instead of measuring in 0 and 1 basis, we would have to measure in the plus and minus basis like we did for the bomb detector experiment, for example, then you would get the information about the phase as well. Again, by measuring 1 billion times. Okay, so this is how we get to know a quantum state once we prepare it 1 billion times, and how do you prepare it 1 billion times? Okay, that's a separate issue. We can talk about that in experiments. That's what you have to do. But here, this is our statement that we cannot copy this. Meaning, if I give you psi and another qubit, and let's say I prepare that other qubit in some known state, say 0, it could be 1, 0, it doesn't matter, but it's known, we say in one state, then what I want is this, right? I take psi and I just copy it over into the other state, and this is forbidden. Yes. All right, proof. Oh, another implication of this that I discussed at the end of the last class was, if I have a quantum computer and I run it once, I get some unknown quantum state. And if I could just simply copy that quantum state 1 billion times, I could learn what that quantum state was, and therefore I would get, a super polynomial, super polynomial speed up, because I would only have to run the quantum computer one time, right? And I could solve, say, factoring problem simply by doing that. Okay, I could just, yes, I'll have to spend some time copying the code, but that's a constant sort of overhead, so to speak, in the problem. Okay. All right. So proof. Okay, let's assume there exists a copying machine, a quantum copying machine, U. Okay. So the idea of this U is I put in psi, put in 0 into U, and it spits out psi and psi. Okay. We're assuming there exists such a machine. Okay. Then, of course, since U does indeed copy, let's assume this exists. Now, so then what we're saying is that U on psi 0 gives me psi. And of course, since it works for any unknown state, let's take one more unknown state, phi, okay, which we also don't know. And the claim is that you must do this as well, correct? And it must do this for all combinations of psi and phi. So let's start first by taking the state U. And of course, remember I've said that, this U has to be unitary and all that to preserve everything. Okay. So let's start with now the state U acting on A and psi plus B times phi. Okay. And of course, 0 as well. So I should say. Well, I'll leave the 0 outside. Okay. So that's our clone onto which we want to copy, or register onto which we want to copy this state. Okay. Well, according to the theorem, we know that U, of course, so on the left-hand side of this, if I were to operate with U, let's first think about what it should do. If I call this whole thing an unknown state, then what it should do is create the state A psi plus B phi times A psi plus B phi, correct? That's what the copying machine should do, because it is a copying machine. It takes any input state and it copies it onto the output state, right? This is what I should get. So we can write out the right-hand side, A squared psi plus A B psi phi plus B A phi psi plus B squared phi phi. So this is what I'm expecting the copy machine should do to some linear combination of psi and phi. Okay. Is this? So that's the right hand side of that expression. What's on the left hand side? Well, on the left hand side, what I have is u acting on the state A psi 0 plus B phi 0. And since this is quantum mechanics and everything is nice and linear, we can just take u inside these brackets. Okay. So u acting on the first one should give me A psi psi. Right? Because I take u in here, acting on the product psi 0, it should give me psi psi. And on the right side, it should give me B phi phi. I hope you're beginning to see the problem. Yes.
Was like the zero shows like arbitrarily, like
Yeah, it could be anything. Yeah. It's some register onto which I want to copy my state that I have. Right? Some extra set of qubits. Right? Just assume I can build as many qubits as I like. Okay. And the point is that for one, let's say I give you one additional qubit, I want to copy the state onto that additional qubit. Okay. Well, okay, so you can look at this to the left-hand side and right-hand side, clearly not equal. There's no way to make them because it has all these products, psi phi, phi psi, etc., that are not on the right-hand side. Okay, so that's it. That's the proof. Okay, very simple. 2 lines. Okay. So, and the only way in which this can be true, that these two could be equal, is if either A equal to 0 or B equal to 0. Right? Because if A is equal to 0, then yes, the output state here is B squared phi phi. Okay. And the output over here is also B phi phi. Okay. So it can't work for any general superposition, is what I'm trying to say. And that makes it a non-valid quantum copier machine. Okay. All right, so we have considered the case of like everything being exact, but what if it was approximate? Okay, I don't get an exact copy. Fine. I had to learn to live with that. Well, but maybe I'm happy with approximate. Just a little bit off. Who cares? Let's build an approximate copy. Okay. So what do I mean by approximate? Well, obviously we have to define something to express that. Anyway, but before I go on, this is okay. This proof, yeah. You can also, there's another version of this proof using linear algebra, using matrices in your textbook as well. You can look at that as also. It's it's equivalent proof. Okay. So I want to say U psi 0, is approximately psi psi. And I'll define what I mean by that in a minute. U phi 0 is approximately phi phi. Okay. So, so we must, of course, for all of this to work, we must have the inner products to be roughly equal. Basically, that's what I'm essentially trying to say. So let us look at the inner product. That's what I mean by approximate, right? Meaning, normally, if I have a state psi, let me write that down in a minute. So if I have psi psi, I'm writing tensor product basically here, psi psi. This is always one, right? That's always one. Because it's inner product of psi with psi and inner product of psi with psi multiplying each other, right? And each of those is normalized to one. So this total product is always one, and same with phi. Okay. Does it make sense? Okay. So whatever the output of this is, call this some state, alpha. Okay, that's the new state that I got from the copying machine. What I'm claiming is alpha psi is approximately one. And you can add some epsilon if you like to say I can make this as close to one as I like with this copying machine without it being exactly one, because that's what the original proof forbade us. I don't know what the right grammar is there, but it prevented us from saying that we couldn't do an exact copy. We can't make that exactly true. So can we do this instead? Okay, we have two states on the output. Okay, maybe we messed up the first state and the second state equally, but such that overall the copying machine is reasonably accurate. Okay, like faxes. In these days, nobody uses faxes, but in the old days, if you used a fax and then you looked at it, sometimes things didn't look so great, right? Okay, so let us start with the inner product. Okay. Okay, so let us start with the inner product. 0, phi. Again, I am starting with the same kind of thing where I have psi 0. Okay, this is my inner product of the two states. Okay, so just taking these two states. Okay, and now I'm operating with this u on the psi 0 and u on this phi 0. Okay, on either side. Okay, so what I want is I want the state. Okay, let me see if I can write this in a little better form. Okay. Let's start with the machine u acting on phi 0. And it gives me some state beta. Okay. And let it act on the state psi 0. And it gave me the state alpha. We want to say that either alpha acting on psi or beta acting on phi is almost one. Okay. All right. So let's see if that can be made true. And also let's look at this inner product as well. Okay. So okay, so let's look at the inner product. I see. Yeah, sorry. Misunderstood. Prove myself. Let's look at this inner. Okay. Before I find this inner product, I'm going to sandwich u dagger u. Why is that? Because u dagger u is a unitary operator. So I can always put it in between any inner products because it's just an identity matrix. So I'm allowed to put that over there. Okay. So, and our claim is u phi 0 equal to phi. Yeah, you can ignore this. It's approximate, but we don't need this for the. It's true, but it's not necessary for it. Okay. U phi 0 is approximately phi. Correct? That's our claim. Which means, and u psi 0 is approximately psi 7. Okay. Then we must have from that proof 0 phi with U dagger on the left-hand side, okay? And then U acting on psi 0 on the right-hand side. From these two equations, this one and this one, 0, phi bra with U dagger is just phi phi with the bra, right? It's just taking the row vector equivalent of this equation. When I take the row vector equivalent of this equation, I must take the dagger on U. Because U is a unitary operator, so when I take its complex conjugate transpose, which I do when I do taking the bra vector, U goes to U dagger. So this whole equation is just phi phi. This whole equation is just psi psi, approximately, right? So we are claiming that the left-hand side, this equation is approximately phi comma phi psi comma psi, which is of course nothing but phi psi whole square, right? It's the inner product in both the qubits, so it's phi psi the whole square. Okay. And what about the right-hand side? Okay. So the right-hand side of this equation, which is I replaced, or this part of the equation, I replaced this thing by U dagger U, right? I said that U dagger U can be put in between in this inner product anytime I want, because U dagger U is identity matrix. But if I just look at this inner product over here, well, that's clearly 0, 0 times inner product phi psi. And this is 1, and this is phi psi. So what we are saying, we have proven is phi psi squared must be approximately equal to phi psi. If this approximate quantum cloning machine exists, we have shown that for any arbitrary psi and phi psi squared must be approximately phi psi. But this is only true if and only if phi psi is either 0 or 1. Okay. So those are the only two values again for which that this approximate cloning machine can work. But if that is the case, that means either phi is identical to psi, which means we have two known states, which we know we can always copy known states, or we have two states that are completely orthogonal to each other, which again is saying we know exactly what phi is. It's known to be nearly orthogonal to psi. So we're saying we can copy the states if they're either known to be, say, 0 or 1 or plus or minus, but we don't, if there's anything in between that we don't have full knowledge of, we can't make even an approximate copying machine. Yes, sorry. Yeah, you raised your hand.
Yeah, so like even if we don't know the state,
Yes.
do you know they're orthogonal?
Yes. Then we know what the state is.
Even if we don't know exactly what they are, you know that they're orthogonal.
Yeah, because if it's 0, if I tell you one state is 0 and the other is orthogonal to 0, the only other state that's orthogonal to 0 is 1.
What if you don't know either?
Well, then it's an unknown quantum state. So you don't know what it is.
Is it possible to not know either state but know that they're orthogonal to each other?
Yes, you can always verify that they're orthogonal, right? By taking the inner product. Oh, you mean to say if I don't know what the state is at all?
Right.
Okay. Well, then you don't know. Yeah, you can't find out anything about it, right? Yeah. Yes.
So in this example, you figured that the copying machine also destroys the original qubit a little bit. I was wondering the cases that the original qubit is
Preserved.
Yeah.
Yeah. Okay. Yeah. That's just a renormalization, so to speak. Yeah. It doesn't affect what I said. Yeah. I just changed the error to be, epsilon over 2 to epsilon or something like that. It works exactly the same. Okay. So we have ruled out two possibilities. Oh, you have a question? I thought you were raising it.
So like when we applied the U with the dagger
Here?
yeah
Yeah.
that's the U on the other side. That was like equivalent to what we had above.
Right, the two sides are equivalent. This statement and this statement are identical to each other. But I have derived two contradictory results from the two sides of the equation.
So like the next line down
Yeah.
is that also equivalent? Sorry.
Yeah, that's just the action of U on the state 0, 5. That comes from here. So, oh, sorry, I erased it. Here. So U acting on phi 0 is approximately phi 0, or phi 5. Which means from this statement, flipping everything over to the bra side, phi 5 U dagger must be equal to phi 5 approximately.
Okay. So
Yeah, sorry, phi 0 with U dagger must be approximately phi 5. So this statement is equivalent to this statement. Does that make sense? Yeah, so to reiterate the chain of reasoning, I started with this inner product, okay? And this one, I replaced this vertical, which is an inner product, with U dagger U, which I'm allowed to do because that's an identity matrix. Okay, and then I said the left-hand side, this half, is equivalent to this one. So therefore, the output must be approximately phi 5 on the left-hand side or the bra side. And the ket side, U psi 0 is approximately psi psi, according to this machine. So this must be psi psi. So from these two results, we derived that this must be equal to phi psi squared. Okay, but the left-hand side, if you like, of this identity is this statement, and that is easily seen to be just 0, 0 times phi psi. And 0, 0 is 1, so this left-hand side is simply phi psi. So we said the left-hand side and the right-hand side are approximately equal to whatever approximation you want, but that ends up being a contradiction. That would not be true unless we knew that either phi was identical to psi or we knew that phi was orthogonal to psi. And those are the only two situations in which we can build a perfect copying machine, or approximate copy. Okay, I think that's it as far as proofs go. There is one other situation that people often think about. I don't know if you've wondered about that already. So I said U is a unitary machine. Oh, somebody might ask something. I've only considered unitary machines. What about yes, other machines? Non-unitary. Thank you. That's what I was looking for. Yes. Why can't we have some machine that does some measurements in the beginning or during the machine, sandwiched between lots of like unitaries and whatever, you can be as complicated as you like. I don't care. Because the ultimate goal would be like golden, right? Be like a copying machine that works even approximately. Could there be a machine that takes measurements in between and I mean, it's a non-unitary machine, obviously, because it has measurements, and measurements, as we know, destroys the probabilities, as we've seen. I mean, destroy means doesn't preserve anymore the state of the machine. But maybe by some clever combination of measurements and logic gates and so on, we could like build something that was approximate quantum machine, approximate copying machine. Okay, so that proof is longer, more involved. Maybe I'll try to lead you through some steps of it in an assignment or something. But yes, you can also show that machine doesn't work. Okay, it also leads to contradictions. Or the other way to say it is that machine, which has buried inside it internal measurements and so on, can be made to look like a unitary machine followed by some measurements. Okay. And that immediately again brings back our proof, which says that we can't do it with a unitary machine. So any machine with lots of measurements on the inside can be made to look like one unitary matrix followed by a bunch of measurements. And therefore, again, we have not preserved the state even approximately because the unitary machine, as we've just shown, cannot preserve the state approximately. So again, we rule out that possibility. So that's the sort of the overall view of the proof. Obviously, I'm not leading you through all the steps of the proof here, but yeah, you can. Okay, so all right, so that's it as far as today's lecture part goes. So I think we'll have some fun with quantum computers now, quantum programming. And then I have in the last 15 minutes, if I can get your attention to try out, we are going to do another tutorial on qubits and gates and so on. So at the last 15 minutes or so, 20 minutes of the class, I will hand out this quiz. It's an initial quiz just to like see where your state of understanding is, just like we did for the last time. And then we'll do a tutorial and then we'll do a post test quiz. Okay. Okay. We go. I show that here. Okay. Okay. Very good. All right. So when you log into IBM on your tablet or PC or whatever, you should probably get something that looks like this screen, right? And want to follow along, maybe? Okay, so if you look on the left-hand side and then click on that little thing, you'll see the following, tabs. So first we can look under Quantum Composer. Oh, no, sorry. Okay, I see. Okay, very good. That'll be work. Okay, just a few minutes ago. Up there. Okay, very good. All right, so hopefully you all see this when you open up your IBM. Another thing to know just before we get started is up here is the compute resources that are available to us. Okay, and if you're part of the education group for this course, then you should see a whole bunch of things. And one nice thing is you'll have no limit on the number of jobs you can do on these machines. Okay. But of course, we're still in a queue with a lot of other people. So it might take some time to execute the machines. As you can kind of see the list of jobs that are pending right now. Okay. All right. So going back up here. Okay. Oops. Quantum Composer. Let me see. Was there anything else on quantum? That's it. Okay. Composer.
exchange.
Okay, exchange. Okay, so let's see. So as you can see, the outline is very similar to the quirk stuff that we've been doing. There are 3 or 4 qubits that we can work with right now, and we have a classical register of 4 bits onto which we'll read all the outputs. Okay, so when we make measurements, we will read them out here. So let's start with something very basic. I'm going to show you, and which is, let's make a Bell state. Okay, so I drag a Hadamard onto the bottom wire, or ignore these 2 qubits for now. You can even get rid of them if you want. And just delete them if you want to do that, which maybe we should for this starting thing. Yeah. Okay, so we just have 2 bits and 2 qubits and 2 classical bits. Okay. And so I put in a Hadamard here on this, and I'm now going to bring a control NOT gate onto this. But now notice the control NOT gate is the C0. Which one is this? This is the left qubit is the target, and the right qubit is the control. That is C0 01, right? So that's not what I want. I want to change this. I just push edit over here and switch the controls and the target. So I say control this, and it automatically knows then that the other one must be the qubit that's controlling it. Okay, so that's our first starting circuit, just to start with. And let's look at the outputs over here. First of all, this is all, simulated probabilities. Okay, so it's saying that you can expect that roughly about 50% of the time, if you go and hover over here, you can see 50% of the time we're expecting to be in the state 0, 0, and 50% of the time we're expecting to be in the state 1, 1, okay, which is an entangled state 1 over root 2 of 0, 0 plus 1, 1. This is an entangled state. Now, so far, this is just a simulation. It's not an actual quantum computation. Also, there is a nice thing which I've seen it. I know what they're saying, but I don't really use it that much. So I'm going to switch the panel over here to state vector. And there's a skew sphere, which is another way of visualizing multi-qubit states. It's kind of useful at times, I think, but I don't know. I don't use it that much. So I'm just going to remove it from the panels. We can come back to it. I kind of see what they're trying to do, and I like it. It's just, something that I haven't used much. We'll come back to it. I understand what they're trying to do, so I can explain it to you later. Okay, so now we see here, this is the state vector, which is meaning the state, the qubit state. And now we can, if we were to change, for example, this one, if we initially put an X gate to make this not a 0, but a 1, so that we could see what happens. There. You see how this turned red over here? The red column, which means it's a state vector 0, 0 minus 1, 1. The phase is given by this color coding over here. So we can just read off, okay, it's a pi phase. A pi phase is e to the I pi, which is minus 1. Okay. That's the red color. And then, of course, in between other colors as well. Okay. You can also look at these phase disks, as they're called. It's not so useful here because, as we know, this is an entangled state. And if you remember from the quirk simulations, in entangled states, the individual phases or the individual qubit state doesn't have much meaning anymore because the individual qubits are not in any particular qubit state. So, so you can see the phase is 0, The probability though is 50%, and there's something called the purity. I'll explain it when we get to entanglement, but it basically is saying that purity of 0.5 is a maximally entangled state. Okay. And 1 is a non-entangled state. Okay. It's just something to know. Okay. So the purity, if it's 0.5, then this is in a entangled state and it's maximally entangled. If it's 1, it's non-entangled. And if it's that's the range for it, between 0.5 and 1. And if it's in between 0.5 and 1, then it's entangled, but with some less than maximal entanglement. Okay. So this is an additional sort of output that they give you. Okay. Of course, you're also free to play with single qubit gates like we have done before. So maybe we start with that. So, okay. And okay, so let's start with some state Z. Okay, and so when I put a Z state over here with a 0, well, okay, that does nothing. All right, so let's try adding this again, not gate. Okay, now what it shows you is if you hover over the phase disk, you can see now the phase is pi right there, and the probability of being in the 1 state is 100%. That's because the Z gate just switches the phase from 0 to pi, right, on the 1 state, but does nothing to the 0 state. So that's exactly what the output is over here. Okay. Any questions so far about this circuit composer or quantum composer? How it works? Okay, let's build back our circuit. I keep doing this, doing the quirk thing of dragging things back. Okay, all right. So let's bring back our circuit. Okay, so far we've just been, doing things that we understand fairly easily. So, but let's run a simulation on the machine. So we could do setup and run, and we can choose one of the machines over here. Okay. All right. So before I do that, let's go back to the resources tab, the compute resources. And remember, there were these machines that we had seen that were available to us. Let's double click or click on those machines to understand what their details are. Okay. What is this machine? Yeah. Okay. So you can see here a little bit of information about the machine. It has a total of 7 qubits in the machine. It has a 32 quantum volume. Okay, these are more technical indicators that you don't need to worry too much about. Just talking about how good of a quantum computer is it. Here are some of the basic gates that it can do that are built into the machine. Okay, some of them you might recognize. CX is control X, which is C naught, right? Then some of these you may not recognize, like RZ and ID and so on. And then down here is actually something quite interesting. This is the topology of the quantum qubits. That is, this is how they are connected on the chip. Meaning, you can see from here, doing a NOT gate or C naught gate between 0 and 1 is fairly easy. Between 1 and 2 is fairly easy. 1 and 3 is fairly easy. But if I want to do 2 to 3, or 0 to 3, well, what I have to do is, first I have to do 1 to 2 C naught gate, then do a swap operation between 1 and 3, and then do again a swap operation back. Okay, so this is how I would create a C naught gate between 2 and 3, or 0 and 3. Okay, now, of course, that's a lot of things to remember for us. We would have to keep looking at this topology and figuring out exactly what we want to do, and luckily that's all handled first. So when we write this high-level code that we did just now of like the circuit composer by just dragging, our various graphical elements, and when we set it up to run, the processor will understand what we're trying to do and create a new circuit. And that new circuit, for example, if I told it to do a C0 gate between 3 and 2, will decompose itself automatically into the right combination of operations to give us the C0 between 3 and 2. So that's called a transpiled circuit, and I don't know if we'll see it because sometimes it takes a long time to run. So let me try it out and let's see what happens. Okay, so that was everything here. Was there anything else I wanted to talk about here on this first circuit? Oh, yes, well, at the end of the circuit, we want to measure something. Okay, now in Quark, we didn't have to do anything. Quark automatically measured at the end of the circuit what was happening to the qubits. But in a quantum circuit, we want to specify everything. So we have to specify, I want to measure at the end of this. Okay, so here is the measurement block over here. So I just take that. You can see it measures C and it puts it in the 0th qubit, 0th classical bit of my register, which is what I want. And similarly, when I do that, it measures the one state, the first qubit, and puts that in the one bit, the second bit, the left bit of my register. Okay, so that's enough now to set up our full simulation. So we can go here and do setup and run, and we can choose between many different computers. So for example, I could pick, say, this one. Okay. Or what's probably most useful at our stage, since we are running somewhat low on time here, is to use the QASM simulator. Okay, so what this does is it's not quite the same as the quantum computer. It runs it with like some pseudo-random measurement probabilities. Okay, so that's what this is doing. And actually, I should have mentioned that also as well. So the probabilities that you see over here, for example, right, when it tells you that these are probabilities, it's actually running the experiment for the visualization, just for the visualization, with a seed which you can change. So, for example, you could run this with a different seed. Let's choose 317, 117, right? Yeah. Okay, and okay, it's a maybe, I guess I should have pointed out. So now things are slightly different on the probability. So you notice that, actually, this is important to notice. So not only are the probabilities different, you notice now the answer is always 1, 1. Whereas earlier, before I put the measurement states here, so let's remove the measurement states so that you can see the difference. Now you see, we have both. Both of these are highlighted. There's bars on both. That's because it hasn't actually measured anything yet. So it's calculating or simulating what the amplitude of the different states are. So as we expect, it should be 0, 0, and 1, 1. And the probabilities are basically like a theoretical probability, right? So when I do the visualization seed and I put in measurements now, well, as expected, when I measure, I collapse the qubit into one state. And you see now it's in the 1, 1 state. So it's in the 1, 1 state, but it does sometimes measure the probability over here. See, over here, its probability is now 51.7% to be in the 0, 0 state and 48.2% to be in the 1, 1 state. Okay. So this is the visualization of the probabilities and the state vector and so on. Okay. So now we can go and actually set up and run this in one of the machines, or we can run it on an IBM quantum simulator, which is over here. Okay. And you can see what are some of the things that you want to look at here. Well, obviously you need to select the machine, and you can even see the details of the machine and so on. But then the other thing you'll notice is 1024 shots. What it's saying is, I'm going to run this circuit 1024 times, measure each time the output, and I'll plot the probabilities after that. Okay. So you can change this number. Obviously, that will just make you have to wait much longer. Okay. So, but here it's fairly simple. So we ran it, and so it should be completed here if you look at the jobs. Okay. See, jobs sent to IBM quantum simulator. I mean, you can click on it. It's running. So even the simulator is somewhat, see when it finishes. Usually finishes faster. Finish. I think it is different now. So these numbers are different, I think. So you can download the whole thing onto your computer and take a look at it. Okay, what else did I want to say? So we have a lot more to say, but we're running out of time here. So let me. Now it's completed. Oh. Okay, now we can see that. Sorry, I was wrong. So let's make that. So once it's completed is when you get this, this panel with all the results from the actual histogram, and you can see here it had an outcome 1-1 with a frequency of 531 times. This is 493 times the total, results. Let's see. Can we see some details here? There are 1024 times. Yeah. Yeah, I think that's about it here. That's what we want to do. So from this, you can extract your own probabilities. Okay. And you can download the whole file like I just did, but earlier it wasn't actually completed. So I was being in a bit of a hurry. Okay. All right. Oh yeah, if you want to view this, I think you can view this. Yeah. So everything else. I think I just did this before. If I hide everything else. This is a better way. This is ridiculous. This isn't quite. What did I do? Yeah, that did. That looks more promising. Yes. Okay. So I guess I had to click that right at the beginning. Okay. So yeah, that makes it a little bit bigger. You can look at it. All that stuff. Okay, let's go back. That's it. You turned off everything. So. Good. A few more minutes here. Let's see what else can I help. Yeah, I'll just briefly mention this maybe. Okay, so if you look on the right-hand side, in addition to the graphical interface that we've been using, there is a code sequence, which is over here, which is written in something called OpenQASM. That's just Open Quantum Assembly Language programming. It's really not assembly language, as you can see. It's more like, you should think of it like the hardware description language, HDL, that you might have used if you have done any electrical engineering courses in that. So it basically describes, I mean, and you can kind of read it off here. So there's a quantum register with 2 bits, there's a qubits, there's a classical register with 2 qubits. And then we're saying do a Hadamard operation on the first, the left qubit, and then do a CX operation on, that is the control X or control NOT operation, with the qubit 1 as the control and qubit 0 as the target, and then measure qubit 0 to the bit 0, to the classical bit 0, measure qubit 1, and store it in the classical bit 1. So it's fairly easy to read, I think, there, and we'll do an example. So one thing I should mention is we have included right at the top here a header file. You can think of it like a header in C or anything like that if you're programmed in C. And this header file basically has the definitions of many of these things. Some of these things are primitives. Some of these, like CX, for example, is actually not a primitive. Okay, and Hadamard is not a primitive either. So it turns out that the primitives in this OpenQASM are a little bit, more simple even than that. And if you wanted to write without their standard header, then you would have to create your own functions or gates yourself, and from the primitives build up your gate. Okay, which I mean, you can do, but honestly, I just use the QE lib1.inc. Include that, and you're good to go. But if you want, we'll go through an example. Maybe I'll do one example of how to make your own gate from the primitives so that you know how to do that. But most of the time, we just include that and then keep programming in QASM. And then, as I'll show you, there's an even higher level language called Qiskit, QIS, Kit, KIT. So that is a higher level Python-like language, or it's basically a Python notebook. And then you can just import all the packages from Qiskit and then program, right? You can do it on your machine, but most likely you'll do it here so that you can set up and run the simulation and stuff like that online. But you can also do it from your own computer. You can download Qiskit and then you just need to supply the right credentials and so on, and then it'll run it on the original hardware. Okay, so we'll talk about that in the next class. All right, any questions so far? I wanted to do 1 or 2 more circuits, but I think we are sort of out of time. So I'll do the next circuit, which is kind of a little bit more interesting than the Bell state. We'll do 1 more like that, just to see what that looks like, and then we can go from there. Okay. So for today, I'm going to just stop, and sorry, we're already out of time. So let me just pass this around. Sure.